Hi, I'm Mr. Rose, and today we're in the home edition of Conservation of Momentum. We're going to go through two examples today. The first example I have drawn out here, an abbreviation of the question. We have a 3 kilogram block that's compressing a spring that's compressed 0.4 meters from equilibrium. It's going to collide into this 1 kilogram block that I have drawn to the right. And what we want to find out in whole is A, after I compress the spring, this spring is obviously going to apply a force. I want to know what the force is that is applied, the maximum force that is, that's applied on the 3 kilogram block once that spring's at rest. Once the spring is released and the 3 kilogram block starts to move, I want to know the speed of the block once it reaches where the spring is at its equilibrium. And I just called that uncompressed distance L. That doesn't really actually matter. I want to know after the two blocks collide, the velocity of this 1 kilogram block is going to continue at 6 meters per second. I want to know what is the speed and the direction of the original 3 kilogram block. And eventually, what I have labeled as part D, I want to know where the block or blocks end up. So what do we have here? A lot of it is very simple, straightforward conservation of energy, conservation of momentum. The very first thing I'm doing is I'm just applying a maximum force, so I don't need to do any type of integration. I know force is equal to K times X, where K is the spring constant of 300 newtons per meter. I want to stop for a second. I suggest, as always, that you have paused already and solved this prior to looking at my solutions. Continuing now, I know I did not need any integration because I'm just looking for that one maximum force. The spring constant was given 300 newtons per meter times the compression distance of 0.4 meters. That's just straight plug and chug to get a maximum force of 120 newtons. Once that spring is released and the 3 kilogram block starts to move, I know that that block is going to be moving at a maximum velocity at that distance. Now, I also said in the question that it was frictionless, so it should continue at that distance, which is why the distance between the two blocks doesn't actually matter. So using conservation of energy, I know the maximum elastic kinetic energy, or elastic potential energy rather, is equal to my maximum kinetic energy. 1/2 kx squared is equal to 1/2 mv squared. My 1/2s cancel. I can rearrange my equation to have a velocity equals the square root of k, my spring constant, the compression distance x squared divided by the mass, and I get the velocity of that 1 kilogram block to be 4 meters per second. Part C, I want to know, again, what is the velocity of the 3 kilogram block after the collision? So since I'm looking for velocity, I'm looking for magnitude and direction. I'm going to use conservation of momentum here. Here, I only have the initial mass and the initial velocity of the 6 kilogram block because I knew that 1 kilogram block was at rest. I just didn't include it because I know that initial momentum is 0. So that is my total momentum before. This is my total momentum after the 6 kilogram block and the 1 kilogram block. So I know my velocity of the 1 kilogram block afterwards, or after they collide, is my initial momentum, m1 naught times v naught, minus the momentum of the second block, the 1 kilogram block, m2 v2, divided by that mass of my first block. I get it 2 meters per second for my velocity of this 3 kilogram block, which means after it collides into this 1 kilogram block, it's going to keep going. It also tells us that it is an elastic collision. In other words, if this velocity is different than the given 6 meters per second after they collide, I know they're not together. If this solved out to be 6 meters per second, just like the 1 kilogram block, they'd be stuck together and moving at the same velocity. So I know this is an elastic. They collide, one goes, the other one keeps going, just not as fast. They collide, and they both keep going separate, elastically. Part D is just a quick review of kinematics. I want to know how far away it goes, so the first thing I do is find the time down. I gave you the height of the table is 0.7 meters, so we know the time down is the square root of 2d divided by a. I use that in my general distance equation, d equals vit plus 1/2 at squared, where horizontal acceleration is 0. So I know my total distance where it hits the ground is 2.27 meters. We just pause for a quick set change, and I'll be right back. Okay, so here I am, new place as I continue to look for better places to record in Casa da Rose. You can see my picture. Here I have a picture of a dog on a boat, and the dog and the boat system are some distance to shore. Let me give you things that I know. My given information, I know the mass of the dog is 4.5 kilograms. I know the mass of the boat is 18 kilograms. What I'm defining, D, is the capital D is the distance between the center of mass, or the distance between the center of mass of the boat dog system and the shore. That's 6.1 meters, if you can't read that. And I'm going to say the dog's going to start to walk towards shore. And the dog's going to walk onto the boat a distance of 2.4 meters. What we're trying to figure out is the distance between the dog and the shore after he walks this 2.4 meters. So as always, I'd like you to try and pause and solve this problem out. If you have no idea where to start, just watch for another few moments. Things that I know. I know that the momentum of the entire system has to be conserved. The momentum of the dog-boat system is obviously conserved. That's the law of conservation of momentum. Now, one of the tricks here is the center of mass between the dog and the boat. That actually doesn't change. And why doesn't that change? Because basically what we have is the dog is running towards the shore. The boat is going underneath the dog, so moving underneath the dog almost like a treadmill, which means the center of mass of the boat-dog system remains the same. That's one of the keys to this problem. So just for my own definition, so we can follow along, what I'm going to do is I'm going to let delta xb be the total displacement of the boat after the dog is walking. I'm going to let delta xd be the displacement, or the distance, I should say, between the dog and the boat, the dog and the shore. That's what I'm trying to find, that delta xd, the displacement or the distance between the dog and the shore. What I know the change in center of mass is 0. So I'm going to find the distance the dog moves with respect to the boat, this delta xd. Well, I know my boat is going to move delta xb, that's the distance that my boat moves, the displacement of the boat as the dog walks, as I defined above, minus how far the dog walks. Again, the dog is walking 2.4 meters forward. The boat is going to move underneath the dog. So I'm going to find this as the distance the dog moves, delta xd. I'm going to, with that, use conservation of momentum of my entire system. I know the mass times my distance. I know my center of mass is not ever changing. That's going to be 0, is equal to the mass times the distance of the boat plus the mass and the distance of the dog. What we're doing with that is I can see how I dropped my delta xb. This is the distance the boat moves. This is the distance the boat moves. And I dropped the delta because I'm just going to set my initial condition at 0. Makes it a little bit easier for me. Just one less thing to carry around. So I'm finding the center of mass. What's changing is 0. I know the boat moves. I know the dog moves with respect to the boat. And I know that conservation of momentum, I know the whole thing isn't going to move. That's why I can use this conservation of momentum theory. What I do here, is now I can plug my numbers in and I can rearrange my variables and I can solve for delta xb. I know 18 times the displacement of my boat. 18 was the mass of my boat. I know 4.5, and then again, this was the displacement or the distance the dog moved with respect to the boat. Rearrange, solve for the distance the boat moves is 0.48 meters. Now I can put it all together. I can figure out how far the dog is from shore. The total distance that they started with, 6.1 meters. The distance the dog moves, 2.4 meters. And the distance the boat moves with respect to the dog as the dog is walking forward, 0.48 meters. Put all of that together, we get a total distance, the dog to the shore, of 4.18 meters or 4.2 meters. That's all I have for these examples. I hope you followed along. I hope you understand how I was utilizing conservation of momentum there. It's not an exact conservation of momentum, but it's an application of it for that center of mass. Again, we know the center of mass is not moving. Again, that's all I have. Please feel free to like, comment, or subscribe, and I will see you next time.